Hello students, in the last session we completed four different quantum numbers: principal, azimuthal, spin, magnetic quantum number, right? And same way we did see the filling of electrons in monoelectronic atom and then the Aufbau principle, right? So these were the concepts that we saw in the last session. This session will also be shorter. It will take around like 30 minutes, that's it. So in this session you will see Pauli's exclusion principle, Hund's rule, like two different statements that you need to know. Finally, we will also see that electronic arrangement, got it? Electronic configuration with respect to the element, a basic understanding, we'll see that one. And we will see like nodes, what is meant by node, how is it related to the orbitals, and how to find the number of nodes in different set of orbitals. That part will be done. Finally, we will see a law which is like Heisenberg uncertainty law. That one will also be done, right? So all those things are like an easy stuff that we are going to see in this session. First, let us see what is meant by Pauli exclusion principle. I've given you the statement straight away. Once you read this statement, you'll get the understanding. That's it. No two electrons in an atom can have same set of four quantum numbers. If you're just going to pick an electron, and then if you're going to designate it, it will have, obviously it will have like four different quantum numbers: principal, azimuthal, spin, and then the magnetic, and then the spin quantum number. These four quantum numbers will not be identical for the other electron in that atom. Got it? So if one of the atom have this set of four quantum numbers, the other atom will not the other electron will not have the same set of these four quantum numbers. Got it? The final one, spin quantum number, will be different. At least one of the quantum numbers will be different. That's how it's going to be. Therefore, this statement clearly represents no two electrons in an atom. You can't pick an electron which has same set of four quantum numbers. That's not possible for two different electrons. That's what this principle represents. Got it? It should be clear. It's a simple statement based rule. Then you have got principle. Then you have got like Hund's rule. Got it? Got it? Pairing of electrons in an orbital begins belonging to the same subshell, which means in the p subshell you will have three different orbitals, isn't it? So pairing of electrons in the orbital belonging to the same subshell, let us consider the p subshell, it will not happen, does not take place until each orbitals are singly occupied, which means px, py, pz. So these three orbitals will be singly occupied, then the pairing will begin. That's how the electron will fill in the atom. Got it? So we'll use this Hund's rule while filling this electronic configuration of d orbitals. Fine. So here I have taken element from 21 to 30. That's how I've taken it over here. So the reason why I took it from 21 is because this is when the filling of the orbital will begin. Fine. First, let me write it for the scandium, which has the atomic number of 21. Right, in the next chapter, which will be classification of elements and periodicity and its properties. Got it? So in that chapter, we will learn multiple elements and the periodic arrangement of the elements. Everything will be learned in the next chapter. As if now I have just taken the element between 21 and then 30. I'll just draw electronic configuration for this 10 elements, right? Between 21 to 30. First, here you have got for the scandium. So I'll have to plug in 21 electrons according to Aufbau principle. First, let me start with 1s. Obviously, that will be the first one. Principal quantum number was 1, and then the subshell was like s. So in this s subshell, the possibility is I'll be able to put only one orbital, which means 2 electrons is possible, isn't it? So 1s2. This will be the first one. Then you'll have like 2s2, 2p, and the number of electrons over there is like 6 electrons is possible, isn't it? So the next one will be 2s2, and then you will have 2p6. Okay, now altogether you have got like 10 electrons. I'm just left with 11 electrons which I need to fill with 3s 3p. Got it? Then you have got 3s2, same way, third shell, and then the s orbital which has 2 electrons into it. Then you have got 3p, again 6 together. Now you have got like 18 electrons, isn't it? Now I have got like 18 electrons. Then 3s2, 3p6, then you'll have like 4s. If you remember that pattern that we have learned, you can go through that video. So if you remember that pattern, after 3p you will have like 4s2. Fine. So the next one will be 4s2. Now I have just plugged in 20 electrons into it, and the final one will be 3d1. So that is why I've given over here electronic configuration of d orbital. P will be easy, S will be is just the first one, and here I'm just going to fill it for the d orbital, then you'll get the f orbital. Fine. So for the f block element, in the f block elements we will learn how to fill in the f block series, as if now this is a kind of basic understanding that I'm giving you over here. So 1s2, 2s2, 2p6, 3s2, 3p6, then you have got like 4s2. Finally I just have to put that one electron, that will give me 21, isn't it? So the final electron will be, you would have got something 3d1. Okay, so this is like 3d1. Now yeah, 1s2, that will give me the configuration of helium. Got it? So that will be the first stable one. Then you will have like helium, neon, and then the argon. Okay, for neon you would have got like 10 electrons into it. So this configuration, when 2p6 gets completely filled, so this will be for the neon. Then for the argon you will have 3s2, 3p6, that will give you like argon. Okay, so this is the stable configuration for noble gases. Do not want to worry about that one, we'll learn all those things in the next chapter. As if now 3p6, when you have got like 18 electrons filled, then that stable configuration is for the argon, which is noble gas configuration, right? Therefore here you would have got argon Ar. Okay, I could write it in this fashion also. Instead of writing this again and again, I can just represent it straight away with Ar, which means that's a noble gas configuration. Afterwards I'll just plug in all those extra missing electrons. Fine. So here first, if I put like argon, which means this is a kind of stable noble gas configuration, which means 18 electrons have been completely filled and it is stable. Then after that you would have had 3 electrons. Fine. So this electron will be responsible for the valency and other stuff. Fine. Do not want to worry about that one. It will also be dealt in the upcoming chapters. Fine. So the for the electronic configuration, the formula is argon, and then you would have got Ar, and then you would have got 4s2, 3d1, right? Either you could write this complete electronic configuration, or I could write the noble gas configuration. After that, how many number of electrons is missing, I'll just put that one according to the Bohr principle. So you could also write it in this fashion, the electronic configuration. Got it? So this is the notation that we use to plug in electrons for that particular element, right? It should be clear. You do not want to have any doubt into it. That idea has to be clear. Then let us see for the different set of elements over here. Fine. So first, let me start with the scandium as usual. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt. It just goes on. You will learn in the next chapter. I'll tell you to memorize like 30 elements. First 30 elements, you'll have to memorize that one. Same way, I'll also ask you to memorize S block elements, D block elements, some set of P block elements. I mean, some part of P block elements and all those things. Got it? As if now this is the element between 21 to 30. I've just chosen somewhere around the 10 elements, and then I'm going to draw the electronic configuration for those elements. For the first one, which is scandium, you have got like argon. After that argon, 18 is done. Then obviously what we will have like 2 electron for the 4s, same way 1 electron for the 3d, right? So the first one is simple. So 2 electron will be in the 4s. So this is the lower level when compared to 3d. Then you would have got 1 electron into 3D subshell. Okay, right? Then for the titanium, scandium, titanium, isn't it? Then for the titanium, you'll have had the noble gas configuration argon. Then you would have got 4s, 2 will be filled. Then I have told you, right? You have got like Pauli Hund's rule. What is meant by Hund's rule? All the orbitals will be singly occupied. Then you will have the pairing to take place, isn't it? So here first everything has to be singly occupied. Then the pairing will begin. So here well, you'll have like 2 electrons in the 4s and 2 singly occupied d electrons. Got it? Then for the vanadium, same understanding, 2 electrons, and then you have got like 3 electrons over there. Then you have got like some different situation over here, which is like chromium. With the case of chromium, what it will happen over here is in nature symmetrical pattern will be preferred. Therefore, all the d orbitals will be singly occupied. Okay, because that structure will be more stable. I'll tell you something called exchange energy after completing this electronic configuration. That will give you an extra bit of understanding to the way I'm just drawing this electronic configuration. Okay, so for here, all the stuff will be singly occupied because when it is symmetrical, that one will be preferred, right? So one electron from the 4s will be jumped to the 3d, and this is how it will get occupied. Therefore here half filled d orbitals will be preferred. Got it? I'll tell you the reason why half filled d orbitals are preferred. As if now, because of exchange energy, what has happened is, because of the symmetrical pattern, half filled is preferred, right? Half filled d orbitals are preferred. Half filled d orbitals are preferred. Then you have got for the manganese. Got it? Then for the manganese, same way. Yeah, you'll have something like this. And then 1, 2, 3, 4, 5, isn't it? Here in the situation, it was singly occupied. Here, this will be paired. Got it? Then for the iron, what will happen? Same way. This one will be paired, and then all of the orbitals will be singly occupied. Then the first one will get paired. Right? You should be clear with the Hund's rule, isn't it? Then for the cobalt, same way. It will be paired, and then all the orbitals will be singly occupied. First two orbitals will be paired. Got it? Next, with the case of nickel, it will be something like this. So 4s will be paired, and then you would have got all the 5 to be singly occupied. First three orbitals will be paired. Got it? Then with the case of copper, this too is an exception. Here you'll have like completely filled d orbitals, because d orbital filling will make it more stable. Therefore, yeah, here you'll have only one singly occupied 4s electron, and then rest all other will be paired with the case of copper. Okay, got it? It should be clear. Then finally for the zinc, obviously everything will be paired. Okay, so this is how you will have electronic configuration for scandium to zinc. Got it? It should be clear. Same simple pattern that I've drawn over here. You shouldn't have any doubt on this. Then we have got the stability of half-filled subshells. Now we will see the reason for the stability of half-filled subshell. Okay, so the first point is something that I've already told you, which is symmetrical distribution of electrons. In nature, symmetry will be preferred. Okay, so that's the first argument that I'm going to make. So first point is symmetrical, got it, distribution of electrons. So with the case of half-filled subshell, what will happen is every subshell will be singly occupied. Therefore, you are having a symmetry which will be preferred in the nature. So that's the first argument that I'm making over here. And the second point is exchange energy, right? So this will be a valid argument. Okay, so with the case of exchange energy, what will happen is, let me draw something like d subshell. Okay, so you have d subshell. In d subshell you will have 5 different orbitals, isn't it? So when all the orbitals are singly occupied, there is a higher possibility and higher chances for this electron to jump between the orbitals of the same subshell. Okay, so here it will not get excited to the higher energy level. Instead, it will just jump between the orbitals of the same subshell. Okay, so here when it jumps, obviously it will release that extra energy. Therefore the possibility for the stability is more. Okay, so that's what I have written over here. Energy released when two or more electrons of the same spin. So when you have like same spin, when it jumps from one orbital to the other orbital in the same subshell, you will have like small energy released. Okay, so that energy release when two or more electrons of the same spin change places in the degenerate orbital. So degenerate orbital actually means you are having same energy level orbital is what is meant by degenerate orbital. Okay, so same energy level orbital means it is inside the same subshell. Okay, so degenerate actually means same energy level orbitals. Okay, this should be clear. Find energy release when two or more electrons of the same spin change places in the degenerate orbitals, which means all the electron will just switch places inside this orbital itself. When it switches places, what will happen is there will be a small energy release. Therefore, that extra energy that got stored into the electron will, in that atom will get released, so the stability will be greater, right? That is what I've written over here. When you have like more exchange of electrons here, obviously there will be more energy released, which is called as exchange energy. So when you have more exchange energy released, when it has more exchange energy, the stability will also be greater, right? So exchange energy is actually the release of energy. Got it? When it absorbs some energy from the surrounding, obviously it will have like, it will go into the higher excited state. Got it? So instead of going into the higher excited state, what will happen is there will be a jumping of electrons within the orbital itself. Because of the jumping of electrons between the orbitals, the energy will be dissipated. Therefore, it will be more stable. That dissipated energy is called as exchange energy. Fine. So when you have more exchange energy, the stability will also be proportionally more. Got it? This idea has to be clear. When it has more exchange energy, it will have more stability into it. Here the exchange energy is actually the release of energy, right? So if it is able, if the electron is able, if the atom is able to release more energy, then the stability will be more, because if it has released, then the energy for that atom will decrease, right? You should get this understanding and the logic that I'm telling you. Then you have got like orbital angular momentum, and then the orbital angular momentum of electron, and then the angular momentum of electron. Fine. Here also I'll not tell you anything that is needed for the understanding. I'll just give you the formula. You will have to memorize this formula. When they give you something Heisenberg quantum number, and they're asking you to find the orbital angular momentum, just you'll have to use this formula to get the result. Just that's it. You'll have to memorize this formula. So the formula that needs to be memorized is root of L into L plus 1. If they have given you the term orbital, then you should have into h divided by 2 pi. Got it? If they are just asking you to find the angular momentum, simply the angular momentum, not including the orbital, then the formula will be root of L into L plus 1 into h. Okay. Here L into L plus 1 will be inside the root, h will be outside the square root. Got it? This is the formula that needs to be memorized. So here L actually represents azimuthal quantum number. Here L represents azimuthal quantum number. You get question from this formula, so we should by heart this formula. Azimuthal quantum number. Got it? This one has to be clear. Then we will see what is meant by nodes. Now let us see what is meant by nodes. I have written the definition over here. The region around the orbital where the probability of finding an electron is 0. Right? So node is the space or region where you will not find any electrons in it. Right? So that space is called as node. Got it? So to get the node for the s orbital, I have chosen a picture over here. So here if you look at this picture, this is like 1s. Got it? So that will be the first shell, isn't it? Then you would have got like 2s, which means this 2s will engulf this 1s. So 1s will be inside that of the 2s node, 2s orbital. Okay. Same way if you consider the 3s orbital, so this 3s orbital will just engulf both 1s and then the 2s orbital. Fine. So that will surround this complete setup. When you have to find the node, with the case of 1s, the possibility is 0 because that's the starting point. So this 1s and the 2, between this 1s and then the 2s, there will be a space. Okay, there will be a space where you will not have, where you will not be able to get the electron. So that space is called as node. Fine. So here the node will be in this position between 1s and then the 2s. You will have one node. For the case of 1s orbital, you do not have any node into it, so that's the 0 node. Got it? So with the case of 2s, the possibility of finding 0 electron will be one region. Therefore, you have got like one node. Got it? Then with the case of 3s orbital, you will have like two nodes, right? So you'll have like two nodes because there will be like two region where the possibility of finding electron will be zero. Got it? So with the case of 3s orbital, you will have like two different nodes. Fine. So the formula, so the generalized formula with which I can actually find this one straight away easily is n minus 1, where n is the principal quantum number. If you just know the principal quantum number, just reduce it by a number 1, you'll end up getting the number of nodes in that particular orbital. Got it? With the case of s orbital, one node is possible because 2 minus 1, 2s orbital. Same way with the case of 3s orbital, two nodes are possible. Got it? Here I'll just represent this node by a term called radial, because with the case of sphere, I know everything will be radially emanating or radially increasing. Therefore, this node is actually called as radial node. You have got one more node. I'll just tell it while studying p orbital. Fine. So here you need to know this kind of node is called as radial node, because when you're just going to move radially a kind of spherical pattern, in that situation I'll call that node as radial node. Got it? Straight understanding. Here it is called as radial node. Okay, so this has to be clear. In s orbital, so here I have just written in s orbital only radial nodes are possible, the other one angular node is not possible. Fine. So in s orbital only radial nodes are possible. Radial nodes are possible, the other pattern node is not possible. Got it? Fine. So you'll have to be clear with the node with the case of s orbital. Then we will see for the p orbital. When you look at this orbital, it should be clear. Yeah, this is like dumbbell shaped, isn't it? So with the case of dumbbell shape, if it is along the x-axis, so here I've just drawn it in a different, I'm just looking at this picture in a different perspective. Got it? This will be x, this will be y, and this will be z, right? The perspective doesn't matter over here. If it was like 2px, then this dumbbell shape will be along the x-axis, right? So obviously that was along the x-axis. Same way here also, it was along the y-axis. Same way here, it was along the z-axis, right? When you look at this node, when you look at this one here, you do not have any other next orbital to end of this one. Therefore, here you just got only one node. That nodal plane is between these two lobes. Okay, so in the point where these two subshell is going to converge, that will be the point where you will have like nodal plane. Possibility of finding electron on this plane will be 0. So this nodal plane is actually called as the angular nodes. Fine. So other than the radial node, whatever it is, everything will be a kind of angular node. That's what you need to know. Got it? So here you have got like three different angular nodes. In the case of the p orbital, if you just look at, if you just consider only one, which is like 2p, then you have got like one angular nodes, right? So that's the understanding that you need to know. Got it? So the number of nodes, to get the number of nodes, I'll just use the same formula, which will be n minus 1. Fine. So the formula that I'm going to use over here is n minus 1. Therefore, for the p orbital, I just know 1p is not possible, right? So 2p is the only thing that is possible. Therefore, 2 minus 1 will give me the answer to be like 1. Got it? It should be clear. I'm just not dealing with the subshell. I'm just dealing with the p orbital. So I'll have to consider only one orbital. When I just take only one p, 2p orbital, one radial node is possible. Got it? So the general formula to find the radial node will be n minus l minus 1. Okay? So the formula over here will be to get the radial node, the formula will be n minus l minus 1. Got it? I know here I do not have any radial node into it. Only one node was possible. That was the angular node, or I'll call it as nodal plane. Got it? Fine. So here n minus l minus 1 will give me the radial node. I know obviously with the case of 2p orbital, radial node is not possible. If I just substitute n minus l minus 1, 2 minus the azimuthal quantum number, which will be 1 minus 1, that will give you 0. So the possibility of finding the radial node with the case of 2p orbital is 0. That's done. Then you have got angular nodes. So for the general formula to get the angular node will be 1. Obviously you have one node, that node should be angular node, right? So the general formula to get the angular node will be L. Got it? Therefore, here 1 will be my answer because azimuthal quantum number for the P subshell will be 1. Okay, so the answer over here is simply 1. So this one actually should match with this number, therefore it is matched, right? This one has to be clear because while doing some I'll not be able to imagine everything. Got it, those lobes and things of that sort. Just if you know the formula straight away, I'll be able to get what was the total number of nodes. That should be the summation of radial and then the angular node. So 0 plus 1 gave me 1. Obviously, the formula for the radial node is n minus L minus 1 and the formula for the angular node is L, which should be equal to 1. Now let me verify it for the 3px. Then obviously same way it will just work out for the 4px, 5px, whatever it is, it will just work out the same way. Got it? Next let me verify it for the 3px. For the 3px, same like that of the 2s. Here this 3px will engulf the 2px, right? So obviously you will have radial node for 3px. Got it? Because this is obviously radially emanating outwards, right? Therefore, here also you will have one radial node, then you will have like one angular nodes into it. Got it? So the radial node over here is this one. So this will just completely surround, right? I've just drawn the lobe, only a part of a lobe over here. So this one will completely engulf this 2px. Therefore, you will have one radial node. Okay, this together will constitute one radial node. Therefore, here in the situation, the possibility is one angular node and then one radial node. Angular node or nodal plane, both are just the same thing. Here, number of nodes will be equal to n minus 1. Therefore, for 3px, it should be equal to 3 minus 1, isn't it? So 3 minus 1, that should give me 2. Fine. Summation of radial node and angular node will give me the total number of nodes. So to get the radial node, what I can do is n minus L minus 1, that will give me 3 minus 1 minus 1, which will give me 1. So one radial node is possible. Obviously one radial node was there. Same way one angular node should be there. Okay, so here with the case of 3px, the number of angular node was like 1. Same way, the number of radial node was 1. Together it constituted total number of node, which was 2. Fine. So you should be clear by this time whether they give you 3px or 4px, 5px, whatever it is, number of angular nodes possible is just 1 because it is just equal to azimuthal quantum number, isn't it? Which is like L. Got it? Then for the number of nodes of 4px, same way this 4px will engulf 3px and then the 2px, isn't it? Fine. I'll just use the formula straight away. Number of nodes will be equal to n minus 1, isn't it? For the n, I'll substitute 4. 4 minus 1 will give me 3. Got it? Same way for the radial nodes, the formula that is needed will be equal to n minus L minus 1, which will be equal to 4 minus 1, which will give me 2, right? So it should be equal to 2. That should be pretty obvious because angular node will always be 1 for the p orbital. Got it? This one has to be clear. You shouldn't have any doubt on this one. Next, we will see for the d orbital. Just first, let me explain it with respect to this diagram. Then I'll just find the number of nodes that will be written in the next page. Got it? So here, if you just look at this d orbital, it was already clear that with the case of d orbital, you have like four dumbbells. I mean like two dumbbells into it, which means four lobes. Got it? This four lobe for this xy plane will be along the xy plane, and then here the possibility of finding the angular node will be 2, isn't it? So you'll have like two nodal plane, which means two angular node with the case of dxy. Same way with the case of dxz and dyz, you have like four nodal planes, two nodal planes. Same way 3d x square minus y square also had like two nodal planes, right? This diagram has to be clear. Then if you just look at this one, this is the different one, which is like dz square. When you look at this, dz square, this nodal plane will be in conical shape. Okay, so here the angular node will be in conical shape. That's it. But still, even in this situation, you will have like two different nodes. Got it? Just by looking at the diagram, it should be obvious that you have got here two different angular nodes which will be in the shape of radial, I mean conical. Okay, so this one will be cone shaped. So here you have got conical shaped angular node, right? This one has to be clear. Now let me use a formula to verify it. So if I do use that one, you'll get the answer straight away. Number of nodes over there. To get that one, the formula that I could use is n minus 1, which will give me, so that one was like 3D, isn't it? So 3 minus 1, that should give me like 2. Yeah, so over here you'll have 2. Then to find the radial node, the formula that I generally use will be n minus L minus 1. I just know you will not have any radial nodes into it, right? So that was the first one, 3D, isn't it? So here if you just use this one, you will have 3 minus L. L is 2 for the d Subshell or orbital. So that will be 3 minus 2 minus 1, which will give me 0. So here it was equal to 0 for the number of radial nodes. Then for the number of angular nodes, the formula was straight away, which was like L. So L should actually match with the number 2. Therefore, the number of angular nodes over here is 2. Got it? So it should be pretty obvious. Summation of radial and then the angular nodes should give me the total number of nodes, which will be equal to 2. Got it? It should be clear. Same thing that we have used for the p orbital. Got it? Then for the 4dxy orbital, same way, I'll use this principal quantum number, which will be n minus 1. If I do subtract those two stuff, you will have 4 minus 1, that should give me 3. With the case of angular node, it should be obvious. L should match with it. Therefore, L over here is 2. So here you will have like 2. Okay, that one is done. With the case of radial node, it will be n minus L minus 1. Here it is like 3 minus 2. I mean 3 minus 4, isn't it? So 4 minus 2 minus 1, that will give me 1. Got it? It should be obvious. Here 4dxy will engulf 3dxy. Therefore, you should have one radial node into it. Therefore, number of radial nodes that is possible over here is 1. Got it? It should be clear. You shouldn't have any doubts with respect to nodes. Got it? So node is nothing but that's the region where the probability of finding the electron will be 0. Okay? So do not want to worry about the understanding and all those stuff. Just I'm telling you the statement. Be clear with this idea. Got it? So the probability of finding electron will be 0 in that region. That is called as node. You have got like two different nodes into it. One is radial node and the other one is the angular node. And then total node is the summation of radial and then the angular node. With the case of radial node, the formula was n minus L minus 1. You should know that one. Same way for angular node, it is just the L, azimuthal quantum number. To get the total number of nodes, that will be the summation of radial and then the angular node, which will be equal to n minus 1. So these are the stuff and the formula that you need to have completely memorized. Okay, that will be handy during the examination to solve the sum, right? You shouldn't have any doubt in the stuff that we have seen, right? Next, only one small part is left, which is Heisenberg uncertainty principle. Now we are into the last part of this session, which is Heisenberg's uncertainty principle. Got it? I'll just give you one statement. That statement in and itself is enough for this principle. So here it clearly states it is uncertain, which means it is impossible to determine the exact position and momentum of an electron. Okay, so this is a microscopic quantity. So it is impossible to determine the position and momentum. When it is a very minuscule quantity, minuscule mass, it is impossible to determine the position and momentum simultaneously around the nucleus. Fine. So this is what you need to know regarding Heisenberg uncertainty principle. So they have given you like one equation based on this statement, which also has to be memorized. So you have got like del x, that will be the position, the change in position, the error in the measurement of position, multiplied by the change in momentum. Okay, the error in the momentum, which will be greater than or equal to h divided by 4 pi. Fine. So this formula has also to be memorized. Fine. So instead of we'll also be able to make one more formula from it, which is del x multiplied by, instead of momentum, I'll be able to write it as m del v. Okay, so you will have del vx, which will be greater than or equal to h divided by 4 pi. Yeah, that's it. This is what you need to know regarding the Heisenberg uncertainty principle, right? Nothing else more to it is needed. Fine. You are just familiar with this formula, that is enough. And they'll give you some numbers, you'll have to plug and play with this formula. That's it. Got it? You should be clear with all the concepts that we have discussed in this session. We just did what is meant by node, the Heisenberg uncertainty principle. Then we did the electronic configuration for the element between 21 and then the 30. Those 10 elements, that's what we saw, right? Fine. And also we did see Pauli's exclusion principle and the Hund's rule, right? You should be clear with all the concepts that we have discussed in this session. With this, the video gets completed. Bye.